This lecture begins probability theory. We're doing the basic on probability theory here. There are two reasons why we cover probability theory in statistics. One is that there are many concepts in the world that involve probability, and we need to have a handle on how we use probability in those situations. For example, anytime we make decisions about the future, we implicitly, that is, probably without saying so, use some concepts of probability. Also, and more importantly for this class, there are aspects of probability theory that we need in sampling. Alright, where we're going with this class is that we're showing you the descriptive statistics as you've done in the previous module, averages, standard deviations and such. And later on, we try to glean information from populations based on samples, and to have a good understanding of what sample information can do for us, we need to have a good idea of probability theory. Alright, lots of you have a good idea right now of basic probability. Alright, we all listen to the weather and say if we're told that there's a 60% chance of rain tomorrow, and if we assume this is correct, and if we could run tomorrow over and over again, that is, we start the clock over and over, and some small differences will appear, okay, each time. Then we would expect that 60% of those runs would have rain. Or if you your beliefs don't allow you to accept that we could run tomorrow over and over again and we would have a different occurrence, let's think of the National Weather Service, and over the years it predicts a 60% chance of rain in particular localities at different times. We could take a sample of all those localities in which it said 60% chance, and we would assume that if they're correct, not assume, if they are correct about their forecasts, then 60% of those localities will have rain and 40% will not. Alright, so it's useful to think of two different kinds of probabilities. One, objective, and the other, subjective. Perhaps after we've looked at both of these, you'll understand that there's not a dichotomy here, and perhaps there's a sliding scale between objective and subjective. But these things are not trivial things, but you need to get an idea of the words, the concepts. Objective probability is something that like a coin toss, right? Perfect little tight example. We could get a coin. We assume that both sides are equally likely to occur, and so we could say objectively, based on that assumption, that there is a 50% chance of getting a head and a 50% chance of getting a tail. Without further information, we have no idea whether, for instance, there's a 51% chance really of getting a head and a 49% chance of getting a tail. So without such information, we'll say 50-50. Okay? There are situations where you might have information. For instance, some people spin a coin. That is, they put the side of the coin face on the side of the coin on the table, and then spin it instead of tossing it in the air. When you do that, you run into difficulties because the sides of the coin, even though they're very small and very hard to see, they're not perfectly parallel. They do this because in the the mint, they need to pop the coins out of the die, and to do that they need the sides just a little bit off parallel. Okay, and so it's known in the literature that there might be on 1960 quarter, the probability of getting ahead might be 55% when you spin it. Okay, sorry. And that brings up the another concept. Part of the objective probability sequence is that we're talking about a sort of a long run frequency concept. Alright, so let's say we have a coin and we toss it 100 times and we record the number of heads. Okay, will that estimate be good or what? Okay, is 1,000 tosses, will that get us a good estimate? Well, 10,000 tosses. Alright, this might be a good time to show you that, so I'm going to pause this movie. So you're thinking to yourself, how can I show this on a computer? Well, I've opened up Excel and I've created a little spreadsheet. In the first column, I've created a formula to simulate a coin toss. And let's say that a 1 showing up in any one of these cells is a head. Alright, 1 is a head and 0 is a tail. Alright, so I have 10 tosses here simulated. I have 3 out of the 10 are heads. Alright, so if I use that particular sample to give me an estimate of the probability of a head or a coin toss, I'd get 0.3. Alright, not exactly the greatest estimate in the world, right? I can recalculate this. Sorry, it's not happening. Sorry, the recalculation key stops the movie and doesn't recalculate. Alright, so I've recalculated and I've got another horrible example. Okay, and let me show you a set of recalculations here. Alright, I'm just entering something into another cell here and it'll recalculate without me having to hit F9, which pauses my video. Alright, and you can see this number of heads moving around. This is not exactly a great estimate. Alright, let's look at 100 tosses. Alright, and here we have 100 tosses. 51 out of those 100 tosses is a head, and so the probability of a head now from that particular sample is 0.51. But let's recalculate, and you can see this number moving around a lot. And sometimes we'll get a number that we know is quite way off, right? 0.44. Alright, so let's extend it to, say, 1,000 tosses. Okay, and here I have my first sample of 1,000 tosses, and again, from this very first sample, 0.471 is not exactly what we'd call close, right? I could recalculate this, and 0.49s are good, but 5.3s are not, and we still have estimates which we know are not close. So here we have sort of a trying to converge on a long-run frequency, and you can see that after a while perhaps we'll get closer and closer. Okay, and just to push it one more step, I've gone to 10,000, and on my first sample of 10,000 I get a 0.5029. Now I'm getting close, right? And it depends on your level of desired accuracy in terms of how close you want your long-run frequency. But with this exercise, you've seen two things. We sort of know what the objective probability is here, right? I've constructed these coin tosses with an exact 50-50 chance of getting a head versus tail, and even when that happens on samples which are large, say 1,000, the long-run frequencies, relative frequencies, the estimated probability of a hit sometimes is not good. When I get to 10,000, it gets better. Perhaps with 100,000 or a million, it gets good. Okay, physically that's difficult for us to do, and we worry about after a million physical tosses of a coin that we might actually change the coin. That's another story. All right, and so the next concept on the other side of the spectrum from objective probability is subjective probability. Subjective probability is basically just a belief. You know, somebody says that in my judgment there will be a 60% chance that the stock market will rise tomorrow. Okay, and the way I've said that, my judgment that may or may not include any recourse to data or information. It could be just a belief, a feeling. Okay. Just like people sometimes bet on horses on the horse track just as a feeling. They like the horse, okay? They don't even look at the numbers or know what the horse did in the past, okay? That's subjective. Of course, a lot of things that we have probabilities for in the real world are somewhere between that. And I gave you that example before of weather forecasting. Weather forecasting is not exactly objective, like a coin toss is objective, but it's not subjective in terms of it's just a belief. Okay, weather forecasts are created with structural models, all right, which have basis in meteorology, physics, whatever, and they know that they can't predict the weather precisely, so they give probabilities to these outcomes. And the question becomes, of course, whether these probabilities are accurate. But if we assume these probabilities are accurate, then we have something that is akin to an objective probability. Okay. So if you're interested in finding out more about probability, a good book to read is a book called Against the Gods. Some people remember it wrongly and think it's against the odds, but it's Against the Gods, by Peter Bernstein, or Bernstein. And it gives you, in the first half of the book, a history of the development of the theory of probability as it relates to finance and aspects of economics, decision theory, forecasting, and statistics. Okay, so it's a very useful book for business majors.